Thanks, Brett. So Synergen was formed in 2007 to start looking at thermal plasma applications initially in the for manufacturing of cyanide for the global gold industry. We started out doing that 2007, 2011. Pradeep and the team at the University of Queensland came on board and helped us develop the technology. And we deployed that at a mine site in 2013 here in Australia, a operating gold mine, and developed that further. And then in 2016, we started looking into plasma-based equipment and applications for toxic waste destruction. And then that led in 2017 and 2018 to start doing this PFAS destruction development technology. And so we've kind of come along on a really interesting journey, looking at multiple different applications using thermal plasma in the chemical industry, in the toxic waste destruction industry. Now we're also looking at hydrogen production. But what we have here is a commercial process for the destruction and mineralization of fluorine, which is incredibly important, as we're all aware, in this market and with the issues that we're seeing with PFAS around the world. So for the technical aspects of how this works, I'll hand it back to Pradeep to continue.
Right. Okay. So the second part is slightly more technical than the first session. I will discuss some of the performance and the chemistry and the reaction systems that is taking place in the plasma destruction. But first thing first, what is plasma? Well, plasma is a state of matter. Just to give you an example, if I have, let's say, an ice sitting in a beaker, if I provide energy to ice, then the water molecule moves away from each other and we get liquid. So the intermolecular spacing of water molecules in a liquid is more than the intermolecular spacing in a solid. Now, if I add more energy to the liquid, the intermolecular spacing increases even further, and the liquid or the water liquid converts into water vapor or gas. The molecules are further apart from each other. What happens if I increase or add more energy to that? Well, if I keep on adding more and more energy to the gas, you will come at a stage where the atoms or the electrons, my apologies, the electrons will get knocked off from the molecule and we'll have a charged molecule. So that system, the charged system, is basically a plasma. The process is reversible, of course. If the plasma system is cooled down, it will come back to a gaseous state. If it's further cooled down, it becomes liquid and then subsequently solid. Now, this plasma form is very, very useful for toxic waste destruction. And SynergenMet is not the only company who have investigated thermal plasma for toxic waste destruction. There have been several companies and technologies in past that use thermal plasma for destruction of highly toxic chlorinated and other chemicals. The reason that plasma is popular for destroying chemicals is because when the molecule is in its ionic form, the reactivity is significantly larger, and that kind of helps the destruction and transformation. So that's a bit of summary on thermal plasma, what thermal plasma is. Now, how does the thermal plasma destroys PFAS? Now, in order to explain that, I will take a slight detour and briefly go through how a conventional process works. And I must say that I'm not trying to compare. I'm not saying that one is better than the other. No, all technologies, in my view, are perfectly good. In fact, some of them are really great. This is just to understand the chemistry of what's the conventional route and what is the plasma route. So the conventional route operates by bond cleavaging. So or selective bond cutting. One would have some energetic radicals or hydrated electrons or other UV, for example, other energy sources to selectively cut the bond. And this bond, as the bond is broken, the molecule fragments into smaller pieces. And as more and more fragmentations are formed, you eventually get fluoride or fluorine, which reacts with hydrogen to form HF. And that hydrogen fluoride can subsequently be scrubbed with caustic or lime to form some kind of fluoride-based mineral. Now, this is just one route. By no means I'm saying that this is the only route. There are multiple routes that have been proposed in literature, and this is just a simple example of one. how does thermal plasma work? And not just Synergen thermal plasma, any thermal plasma for that sake. This works by atomization. See, in thermal plasma, we provide energies. The temperatures of thermal plasma are often more than 2.5, 3,000 degrees Celsius. So at those high temperatures, at 3,000 or 4,000 degrees Celsius, the molecules are instantaneously atomized into individual fragments. Once the molecules are atomized, then these molecules remain in that plasma state for a while. And as these molecules moves away from the high temperature zone, then they recombine back. So the conventional route is based on bond cleavaging, whereas the plasma route is based on rebonding or bond forming again after the atomization stage. Now, during the rebonding, these molecules or atoms will bond with different species adjacent to it and takes different forms and shapes depending on what system it is. If there is a copious amount of hydrogen or H radical in the system, then the fluoride will preferentially try to bind with H to form hydrogen fluoride, and one would get HF, and then that can be scrubbed back to sodium chloride. So you have two different routes to destroy PFAS, selective bond cutting as well as atomization. Both routes have their own advantages in the case of destruction. In the previous slide, we discussed the chemistry of what was happening. Just a brief introduction to the physics of the process. As I mentioned, for thermal plasma-based destruction, one needs a lot of energy. The temperatures that we often talk about is 2,000, 3,000, 4,000, so on. At those temperatures cannot be produced by simple combustion process. So to achieve such high temperatures, one needs an electric arc. So a thermal plasma system is basically an electric arc based process. So what you have is just two electrodes, an anode and cathode, and an electric arc is stuck between those two electrodes, and a carrier gas is flown between those two electrodes. As the carrier gas flows between those electrodes, it acquires the heat based on Joule heating and then converts that gas into a plasma. PFAS is then injected into that carrier gas. As soon as the PFAS is injected, it instantaneously atomizes into individual atoms. And then as those atoms or excited atoms moves away from the hot zone, then they would recombine back into different forms. As I mentioned earlier, if there is copious amount of hydrogen, then they would prefer to recombine as HF. And then the product gas will come out. And that's basically a very brief summary of how the physics of the plasma would now. There are certain presumptions whenever we talk about high temperature processes. High temperature is an ultimate method that can destroy all chemicals. But there are clauses associated with those presumptions. I mean, first of all, the thermal incineration process definitely would work as long as it provides the sufficient or right amount of energy to break the bond. Also, the halogenated hydrocarbons are usually difficult to destroy, and one needs to reform those halogenated hydrocarbons into some non-toxic end products. And the biggest challenge in a typical incineration is air emissions. Suppose one is destroying AFFF, and then even at 99.99% destruction of AFFF, there is a small residual which is left. And that residual will exert a certain partial pressure, and they'll have some emission. Now, when we are talking of environmental regulations of 70 ppt, or in fact, in some cases, 0.01 ppt, and so on, any small amount of air emissions is considered harmful because that becomes an uncontrolled process. So when Synergen gave us the target to develop a process for PFAS, we knew that those are the challenges that one would encounter, and we have to overcome these challenges. And the air emission challenge was the most difficult challenge, given that the plasma system cannot operate without a carrier gas. And if you have a carrier gas, you are bound to have air emissions. So how do we solve that problem? Well, we had three major contributions to the thermal plasma technology that kind of helps us to overcome those three challenges. The first challenge was a relatively easy challenge, that is how to ensure that there's enough thermal energy to dissociate the molecule. To do that, we developed a dosing system which allowed us to dose the molecule straight into the arc zone and that gives the maximum thermal enthalpy associated facilitate destruction. Second, as I mentioned in our earlier slides, when the molecules recombine to facilitate the stabilization of fluoride, we need copious amount of hydrogen. So that's what we do in our process. We provide a very selectively strong reducing environment to facilitate the stabilization of fluoride into HF. And the last one, which was the most difficult challenge, that was to suppress air emissions. One could not suppress air emissions because you can't operate a plasma system without a carrier gas. So to overcome that challenge, we discovered a new way to operate the plasma system. Instead of using carrier gas, we now use a vapor. So a vapor is used to operate the plasma system. And as these vapor comes out of the system, it recondenses back into a liquid. And that kind of prevents any air emissions going out. So the entire process is completely contained. There is no losses. So as I mentioned, I want to go slightly into technical aspects of what's happening here. We talk a lot about the process that takes place at high temperature and what's happening. We often hear the temperature for fluorine or PFAS dissociation is like 1500 Celsius, 1600 Celsius, and so on. So to understand that, what I have here is a thermodynamic plot to show the evolution of species that takes place within a thermal plasma system, both in presence and absence of the reducing environment. So this the first slide here is this animation will show you how the species are evolved in a high temperature condition when there is no presence of any reducing environment or in absence of hydrogen. So this simulation was conducted with one mole of PFAS, and 10 moles of oxygen. That's the initial condition that I sent to my simulator, and then the products that were released were then were estimated and shown on this. Now, to understand this graph, on the left-hand side, on the y-axis, I have mole fraction of the products that are coming out. On the right-hand side, I also have the mole fraction, but the scales are different. On the left-hand side, the scale is 0 to 0.2. On the right-hand side, the scale is 0 to 1. On the right-hand side, you also see this legend here, sum of O, sum of CO. These legends will actually move as new species are generated. So you can actually see this moving up and down as the species concentration increases or decreases with respect to time. And on the x-axis, what you have is the temperature. So we will start with 6,000. As I said, the plasma temperature starts at a very high energy. So when the PFAS molecule is introduced into the plasma at, say, a very high temperature, it atomizes. And then as it loses energy, it recombines. And that's what this simulation will show you, that it starts at 6,000. And as it loses energy, how does those molecules recombine? What kind of byproduct is produced during this process? So I will run this simulation now. So as you can see, at 6,000 degrees, at such a high temperature, everything is in a radical form. So you have O atoms, CO, F atoms, and F2CO. And there are other things which are not shown because their concentrations are very low. Around 5,000 degrees, you can see that this top green line starts to decrease. That means the sum of O is reducing. The blue line is increasing, that's O2. So as you can see, the O2 has now come up on the screen. So O is decreasing, O2 is increasing. But if you look at the blue line, however, that's a fluoride. The fluoride concentration is not changing. We still have fluorine atoms at those kind of temperatures. As we reach around 3,500, the oxygen increases, O is very, very, very low. CO, which was the present, is now dropping because CO2 is coming up. As you can see with the purple line, the CO2 is going up. O is almost very, very small. O2 is very high. The fluoride has gone up a little bit. That is because of the mole balance. As more atoms becomes molecules, the number of moles reduces and you get a mole fraction increase. CO2 starts to drop around 2000. Now we are reaching a temperature of 1600, which is interesting because the fluoride, if you see the blue line, the fluoride has gone down, and we have other fluorine species such as CF4 and the blue line, and then CF2O being formed around 1000 degrees. And by the time we reach around 500, we come to a stable state where you have mostly O2 We have some CF4, CO2, and of course there's sulfur in the system. So SO3 is being formed as a result. So this kind of shows you the trend of what the species are produced as the atoms in the plasma state recombines while it's moving out. Now, there was no hydrogen in this system, so it was free from any reducing environment, of course. There are more small species or other byproducts, but they are below the scale. So the next simulation that I have is exactly the same scenario, but we have a lot more reducing environment. So we have one molecule of PFAS, and then a molecule of hydrogen and oxygen present within the system. So once we run the simulation again at high temperature, you can see that there's only H atoms, O atoms, F atoms, CO, HF. Now, in the previous case, the fluoride was constant for a very long time. But here, as you can see, in presence of hydrogen, the light blue line, the fluoride starts to drop very early on. And you can see a dark blue line, which is HF, starts to form very early on. So the fluorine concentration of fluoride atoms becomes very, very low very quickly. HF, on the other hand, increases very rapidly. So, which is a good sign because that allows us to stabilize fluoride. You can also see this OH formation, hydroxyl radical formation at around 4,000. The hydrogen H atom starts to drop around 4,500, which is a light blue line. The fluoride is already quite high. HF is already high. Around 3,500, the hydroxyl radical starts to drop and H2O starts to dominate, which is the water molecule. We'll have more water molecule coming in on the top, as you can see, very quickly rising. The fluoride is the next in the queue, and all the other small products also are forming. Now here, the fluoride is already stabilized. There's very little risk of byproducts because you can see HF is so high, it's so strongly dominating the entire process. The risk of forming byproducts is very, very, very negligible. The other products that you see is, of course, CO2. You have some hydrogen because if you have a reducing environment, you might have some H2 and CO formation. There's very little CO, but there's more CO2 here because there's enough oxygen in the system. So that's what you see basically with this plot. I was trying to explain that the big difference addition of a reducing environment makes to the entire process. I'll quickly run and show you the schematic of how the plasma process works for PFAS destruction. What you see here is electrically energized plasma torch. The PFAS pollutant and the plasma vapor is fed into this torch. And at this area where the PFAS is going in, it destroys, converts into atoms. As the atom goes through the quenching unit, it recombines into stable form. Mostly HF is collected in this tank. We feed sodium hydroxide and it goes through the scrubber. So all the HF that is produced stabilizes to sodium chloride, and that sodium chloride then ends up into this tank. So it's a very, very basic process. The process is not complicated at all. The pressure is atmospheric pressure. You don't need high pressure because the temperature is obviously extremely high. The residence time is of milliseconds, not micro, sorry, milliseconds. So we get a very quick conversion, and that makes the footprint of this entire process quite small. So yeah, that's a quick summary. I'll hand over to Chris, who will talk about his future plans.
Thanks, Pradeep.
Sorry, I just have some water now.
That's right. So off the back of all of that test work and all of the amazing work that's been done, Synergen setting up a destruction facility here in Brisbane, in a suburb called Wacol. In fact, we're coming to you in this webinar from our Wacol facility. And so we're setting up this treatment system and the ability to actually turn it into essentially a manufacturing center to destroy the PFAS and clean everything up and then recycle and then continue the process. We're already seeing that there's a significant level of interest in what we're building here, given the growth of concentrates and the growth of the understanding of the contamination that's existing with PFAS in liquid. And in the United States, we're also starting to see a very strong level of support. So this is the way we're moving forward. We see this destruction capability as being central to really managing this problem and to provide this service into this community. So with that, we'd like to hand it back to Vikram to take questions, and over to you.
Thank you, Chris and Pradeep. We certainly hope that everyone here has found the presentation insightful. We do have 10 minutes now to address any questions you have provided. Feel free to leave them in the Q&A. And as I go through some of the questions I have here, we'll address those.